Hello everyone, welcome to our technical talk regarding the collaborative research between NETL and Cerebras. My name is Mino Woo, and today I'm going to introduce the development of our latest computation methodology using the Wafer-Scale engine. I believe we are reporting the first engineering problem solved on Cerebras Wafer-Scale engine. The motivation of this work is tied to one of the biggest challenges mankind has ever faced, anthropogenic climate change. The current administration has prioritized the mitigation of the carbon emissions to the atmosphere and aims to achieve net zero carbon emissions by 2035 and a net zero carbon economy by 2050. As a part of the effort, the Office of Fossil Energy and Carbon Management and NETL are developing several new carbon management technologies ranging from direct air capture and plant capture, utilization, and storage technologies. Development of such facilities requires a comprehensive understanding of fluid mechanics and chemical processes. Our current computational hardware and software for modeling these kind of systems has significant bottlenecks that impede the solution speed to such an extent that they preclude their own use as good design optimization, uncertainty quantification, and digital twin tools. If we are to meet the ambitious net zero carbon goals, time is of the essence, and the nation must develop the fastest possible and most accurate tools possible to support the design optimization and operation of carbon management equipment. Migrating our modeling capability to technology like the Wafer-Scale engine is critical to rapid design and engineering, which will reduce time to market and cost for new technologies. In order to understand why the Wafer-Scale engine is so good for scientific computing, we need to understand the principle of locality in physics and how we approximate it on computer systems. One of the most fundamental principles in physics is that of locality. That is, an object is directly influenced by its immediate surroundings, and there is no action at a distance. This fundamental physical property gives rise to physical fields, such as this magnetic field surrounding a permanent magnet. The field can be mathematically expressed through a set of equations in which all quantities have an exact local definition everywhere in space-time, such that there are no terms that depend on non-local quantities. We approximate these equation sets by breaking space up into control volumes. We then approximate any derivative terms by linear equation that are functions only of the local value and the values of the immediate neighbors. This approximation of reality becomes more accurate as we reduce the scale of the control volumes and becomes exact in the limit of zero-side volume. Perhaps the most ideal hardware for these types of systems would be a 3D arrangement of identical processors with enough local memory to store all the field values for a single volume. This system would achieve near flat scaling if the grid of processors were large enough to house the problem of interest, because there would be no need for any kind of looping. By contrast, today's distributed computing frameworks take many tens of thousands of processor cycles to evaluate the same terms in field equations, mostly due to the network latency issues. This brings us to the Wafer-Scale engine architecture. The Wafer-Scale engine is quite close to this ideal architecture in that it is a 2D array of identical processors that can access its own memory and that of its four nearest neighbors in a single clock cycle. In this way, a 3D grid of cells can be broken up into a set of columns in one direction, and each processor can hold a stack of cells. The scaling on this type of system is directly proportional to the number of cells in the memory axis, as this is the only dimension with looping. The Wafer-Scale engine is quite unique as well, because the latest generation contains a grid of nearly 1 million cores, which enables quite a large simulation. The Wafer-Scale engine has four key characteristics that differentiate from the traditional HPC methodology. Firstly, it has a large array of independent and lightweight Turing-complete processors optimized for tensor algebra. Secondly, it utilized a 5-port integrated router that supports single-cycle neighbor memory access rates. Thirdly, it has unique memory structure that doesn't have cache hierarchy and is locally accessible within a single cycle. In addition, the local memory network bandwidth are optimized to allow 2 reads and 1 write per cycle. This allows the most memory-intense linear operation like z equals to ax plus y to proceed at single cycle rate no matter if the data is local or at the nearest neighbor. Finally, the WSE has a data flow architecture, which means that the arrival of data can trigger computation, which ensures that data and compute are always synchronized and minimize wasted cycles. We are testing the field equation solving capability on wafer-scale engine with a simple 3D heat conduction problem. The governing equation is time-dependent and three-dimensional heat conduction equation, and is discretized by an explicit forward time and central space scheme. For the simplicity, we assume that the cell distance in all 3 directions are the same. With the assumption, the equation is now simplified with the constant c. This explicit method is only stable when the 3 times c is less than 0.5. We set a cuboid geometry with a fixed temperature boundary condition for each side. The temperature at left and right sides was set to T1 and T2 respectively, and the temperatures for the other surrounding side was set to T0. We developed a Python API to simplify the programming interface for end users. The general idea is that the API on a host can digest tensor algebra expressions that are written in a format similar to NumPy. These expressions get translated into a control vector and an argument vector that can be streamed to the wafer-scale engine. A control tile then interprets the signals and injects them into the fabric of the WSE, which then act appropriately to do math with local and neighbor values. This mathematical operation triggers the corresponding task defined in a microcode for the worker tile. Since the Python API can coordinate all these procedures, users can simply specify general tensor equations to run it on the wafer-scale engine. This is still under development, and we are preparing a scientific publication. Stay tuned for the website of both NETL and Cerebras for updates. These are preliminary results for a case with 320 million cells consisting of 400 by 400 by 2000 in X, Y, Z direction respectively. The result from WSE was compared to the result of a simple serial C+ code to solve the same problem. We compared the result at the 300th time step, which is at the very beginning of the calculation. The left figure shows the comparison of the contour plot at the cross-section of XZ plane at the center, and the right figure shows the temperature profiles at the center of that plane in Z direction. At this time instant, the result from both WSE and C++ code match very well. We did this initial investigation this way because we found that without parallel computing techniques, the time to verify the solution was very excessive. We are working on modifying an open form solver to generate our verification runs in some reasonable time frame. 800,000 iterations at this resolution takes less than 17 seconds on the WSE, but it would take 2 months on our naive serial verification code, and we would be lucky to get an OpenFOAM simulation to run in under an hour if we had close to ideal scaling. We reached steady solution with small test case with 1 million cells. The result of CS2 is very close to the result of C++ code and the analytic solution. The maximum deviation of temperature in the profile is 1.7 Kelvin, which corresponds to a relative error of 0.38%. Although the C++ code is designed to do the same operations, the result of C++ code is slightly close than that of CS2. We are investigating the cause for these slight differences, but it likely has to do with hardware-specific floating point arithmetic implementations. We are starting to look into this with Cerebras. We estimated the performance envelope of both WSE and distributed processors. For distributed processor, we consulted a study from Fisher et al. From Argonne National Lab. The number of time steps that can be done within a second is calculated by the inverse of the sum of TA and TC, which are the time for computation and time for communication respectively. This represents the blue performance envelope in the figure, where the left and right side correspond to the 64 and 130,000 numbers of distributed processors. The performance of distributed processor is limited by the network latency at the upper part of the blue envelope. On the other hand, the performance of WSE can be estimated by the clock frequency divided by the sum of overhead and cycles complete the arithmetic. The overhead related to setting memory addresses and vector lengths before algebra can be done limits the performance as processor workload decreases. The symbols represent our current measured time steps per second. The value currently measured are approximately 27% off from the ideal performance. This performance hit is the result of power prediction models that are mistuned to our workload and are injecting power throttling cycles into the processor. We are currently working with Cerebras and are confident we can achieve much closer to the ideal performance once we handle the power prediction models appropriately. Overall, a single wafer-scale engine shows outstanding performance against many numbers of distributed processors. In addition to the computation time, this will lead to significant energy and cost savings. In conclusion, we found out that the WSE is a promising technology to substitute the distributed processors for many engineering problems. These simple steps and the development of a user-friendly API has given us the confidence to begin to pursue a full-fledged CFD capability on the WSE. We are taking a series of the matter steps to get to a usable CFD code. First, we are building the capability to write nested loops, reduction to the control tile, and while loops with conditional exits. This will allow us to use any kind of implicit solver we want in the solution process. We will demonstrate this capability by solving the same diffusion equation, but with the implicit Cronk-Nicholson method and a conjugate gradient matrix solver. Second, we will demonstrate the relative ease of the API for setting up and solving fluid problems by demonstrating the solution to an advection diffusion equation within a fixed velocity field. This phase of development will culminate in the demonstration of a fully implicit Navier-Stokes problems, such as a lead-driven cavity flow problem. The goal is to do formation and solve right under WSE and never have to move data on or off the system, and do it with many hundreds of millions of cells. If all of this is successful, we will investigate doing complex geometries and unstructured mesh solutions. In addition, we will investigate hybridizing AI and field equation modeling on this single device. We continue to be very impressed by this new class of hardware. Thank you for your attention to the presentation. For questions and comments, please reach out to either Derek Barnes at NETL or Michael James at Cerebras.